Hey everyone, welcome back for another deep dive. Today we're going to be taking a look at quantum magnetometers.
All right.
And these are revolutionizing the way that we measure magnetic fields.
Absolutely.
And do it all thanks to quantum mechanics.
Yeah, we're using an essay by Jorgo Schneepat as our guide for this deep dive.
That's right.
And you might be thinking, Magneto, what? But trust me.
Yeah.
This is some seriously cool stuff with some really, really mind-bending applications.
Yeah, Schneepat talks about using these quantum magnetometers for all sorts of things, like mapping brain activity with incredible detail to detecting submarines.
Right.
Hiding deep underwater.
That's really quite fascinating.
Yeah, so today we're going to kind of unpack how these devices actually work.
Right.
The different technologies involved, and what kind of amazing things we can do with them.
Yeah, exactly. So let's maybe start with the basic question.
Yep.
We all know magnets, right? They stick to our fridges. They're in our headphones.
Right.
But how do we actually measure the magnetic fields they create?
Yeah. So how do we measure the magnetic fields?
Yeah, well, for a long time, we've used things like compasses and coils of wire. These traditional methods work fine for strong magnetic fields.
Yeah.
But they're not so great when you need to measure something incredibly faint.
Right.
And so that's where quantum mechanics comes in.
Yeah, Schneepat really emphasizes this.
Absolutely.
It's like quantum mechanics gives us a whole new language to understand magnetism.
Exactly. And the key to that language is understanding a few key important concepts: spin,
Okay.
superposition, and quantum coherence.
Okay, so let's start with spin.
Okay.
That's like a tiny magnetic moment, right?
Yes.
Kind of like each electron has its own little tiny compass needle.
Precisely. So imagine that tiny compass needle.
Okay.
Instead of just pointing north or south, it can actually be in multiple states at the same time.
That's
called superposition.
good.
It's one of those quantum weirdness things.
Yeah.
Where a particle can be in multiple states simultaneously.
So it's like flipping a coin and it landing on heads and tails at the same time.
Exactly.
It's kind of mind-blowing.
It really is.
Yeah.
And this quantum fizziness, this superposition, is what makes these sensors incredibly sensitive.
Right.
They can pick up the faintest magnetic whispers.
Okay. I think I'm starting to get it.
Good.
But how do we actually use these quantum properties to measure magnetic fields?
Right. So there's two main phenomena that come into play here.
Okay.
The Zeeman effect and spin precession.
Zeeman effect.
Yeah, it sounds fancy.
Sounds fancy.
It is, in a way.
Yeah.
It basically says that if you put an atom in a magnetic field,
Okay.
the energy levels of its electrons will split.
Okay.
And the amount of splitting depends directly on the strength of that magnetic field.
Okay.
So by very precisely measuring those tiny energy shifts,
Right.
we can figure out how strong the magnetic field is.
So it's like the magnetic field is tuning the energy levels of the atom.
A perfect analogy.
Wow.
And then there's spin precession.
Okay.
Remember that tiny compass needle we talked about?
Yeah.
Well, in a magnetic field, it starts to wobble or precess at a very specific rate.
Okay.
And that rate is directly proportional to the strength of the magnetic field.
Okay.
So by carefully tracking this wobble, we can measure the magnetic field with incredible precision.
So it's like using a microscope to look at the individual atoms of a magnet.
It is incredible. What's fascinating is that this effect, this spin precession, was discovered over a century ago, but it's now at the heart of some of the most sensitive measurement devices ever created.
Wow.
Yeah.
So we're using these quantum properties to measure magnetic fields with a level of precision.
Right.
It's just impossible with our traditional methods.
Right.
But hold on, you mentioned different technologies for these quantum magnetometers.
That's right, and that's what we'll explore next.
Okay.
There isn't just one type of quantum magnetometer.
Right.
There's a whole range of technologies, each with its own strengths and weaknesses.
Oh, wow. Okay, so...
Yeah. That's interesting. So it's like we have this whole toolkit of quantum gadgets.
Right.
Each one designed to measure magnetic fields in a slightly different way.
Exactly.
Yeah.
So let's start with one of the most exciting technologies, NV centers in diamond.
NV centers. That sounds like something out of a sci-fi movie.
It does, doesn't it?
Yeah.
But these are very real. Essentially, you have a tiny defect in the crystal structure of a diamond. Okay. A nitrogen atom replaces a carbon atom, and there's a missing atom, a vacancy next to it, that creates what we call an NV center.
Okay. And this defect can actually measure magnetic fields.
Yes.
How does that even work?
It's pretty amazing.
Yeah.
The electrons trapped in these NV centers have a special spin state that's incredibly sensitive to magnetic fields.
Okay.
And what's even cooler is that we can use lasers and microwaves to manipulate and measure those spins.
Wow.
This allows us to detect magnetic fields at the nanoscale. Nanoscale. So we're talking about measuring magnetic fields at the level of individual molecules.
You got it.
Wow.
This makes NV center magnetometers incredibly powerful for all sorts of applications.
Yeah.
For example, imagine being able to map the magnetic fields inside a living cell.
Right.
Or maybe creating incredibly sensitive detectors for medical imaging.
Yeah, I could see how that would be a game changer.
Absolutely.
Okay, what else is on our quantum magnetometer toolkit?
Well, there's another fascinating approach called atomic interferometry.
Okay.
This method actually relies on the wave nature of atoms.
Wait, atoms have waves.
They do.
I always thought they were like tiny little balls of matter.
That's the classic picture.
Right.
But quantum mechanics tells us that particles can also behave like waves.
Oh, wow.
Yeah. So in atomic interferometry, we use lasers to cool a cloud of atoms down to almost absolute zero.
Wow.
These supercooled atoms act like a single giant wave.
Okay.
And we can use that wave to make incredibly precise measurements of magnetic fields.
Okay, so we have this atom wave.
Yeah.
How does that help us measure magnetic fields?
Right. So we basically split the atom wave into two separate paths.
Okay.
And then recombine them.
Okay.
If there's a magnetic field present, it'll cause a phase shift between those two paths.
Okay.
This creates a measurable interference pattern. And the greater the phase shift, the stronger the magnetic field.
It was like those double-slit experiments you see in physics class.
Exactly.
But with atoms instead of light. Pretty cool.
Exactly. It's a beautiful example of how the wave nature of matter can be used for precision measurement.
Yeah.
And these atomic interferometers are incredibly sensitive.
Wow.
They're being used in everything from fundamental physics research to super accurate navigation systems.
That's incredible.
Yeah.
Okay, so we have NV centers in diamond.
Right.
We have atomic interferometers.
Yes.
What else we got?
Well, they're also squids.
Squids.
Yeah, it stands for superconducting quantum interference devices. And these are among the most sensitive magnetometers ever created.
Superconducting, that sounds like it involves some serious cold temperatures.
It does.
Yeah.
Squids need to be cooled down to extremely low temperatures, close to absolute zero to work.
Right.
But at those temperatures, they can exploit the quantum properties of superconductors to detect the tiniest changes in magnetic flux.
So these are the ultimate magnetic field bloodhounds.
Pretty much.
What are they used for?
They're used for a whole bunch of things. One of the most important is medical imaging.
Okay.
For example, squids are used in magnetoencephalography, or MEG.
MEG.
Yeah.
Okay.
That allows us to map brain activity in incredible detail.
Wow.
By detecting the incredibly faint magnetic fields produced by neurons.
So we've got diamond defects, atom waves, and superconducting sensors.
We do.
What other kinds of quantum magnetometers are out there?
Well, Schneppet also talks about optically pumped magnetometers, and these are becoming increasingly popular because they're very sensitive, and importantly, they can operate at room temperature.
Okay, so no need for fancy cryogenics with these ones.
That's right.
How do they work?
So they use lasers to manipulate the spin states of atoms in a vapor cell.
Okay.
By carefully measuring how the polarization of the laser light changes as it passes through the vapor, we can determine the strength of the magnetic field.
So we're using light to essentially probe the magnetic field's effect on the atoms.
Exactly. And the beauty of these optically pumped magnetometers is that they're quite versatile. You can make them very compact, even portable, which makes them suitable for things like geophysical surveys, where you need to map out magnetic fields over a large area.
Okay, so we've got our NV centers, atomic interferometers, squiotometers, and optically pumped magnetometers.
Yes.
A whole quantum magnetometer dream team.
It really is, and each of these technologies has its own strengths and weaknesses. But the point is, we now have this amazing toolkit for measuring magnetic fields with incredible precision.
Right.
And that opens up a whole universe of possibilities.
Speaking of possibilities, I'm really curious to know what these quantum magnetometers are actually being used for.
Yeah.
Where are they making a difference right now? So we've got this amazing toolkit of devices for measuring magnetic fields.
We do.
But where are they actually making a difference? What kind of cool things are they being used for?
Yeah, so let's start with biomedicine.
Okay.
One of the most exciting applications is magnetoencephalography, or MEG for short.
MEG sounds intense.
It is pretty cutting edge stuff.
Yeah.
MEG allows us to map brain activity in really really amazing detail.
Okay.
It's like taking a high-resolution MRI of the brain's electrical activity,
Right.
but without any radiation involved.
Oh, wow. So it's completely non-invasive.
Exactly. And that makes it really valuable for studying brain development in children or for diagnosing conditions like epilepsy.
That's incredible.
Yeah.
It's like we can see the brain thinking in real time.
It is pretty amazing.
So we've got brain imaging. What other fields are benefiting from these quantum magnetometers?
Well, this technology isn't just for brains.
Oh, yeah?
Quantum magnetometers are revolutionizing how we see what lies beneath our feet.
You mean in geophysics?
Exactly.
Yeah.
They can detect subtle variations in the Earth's magnetic field caused by all sorts of things.
Okay.
Mineral deposits, underground water sources, even archaeological sites.
Wow. So we're talking about finding buried treasure, maybe uncovering lost civilizations.
It's definitely more than just finding buried treasure.
Yeah.
We're talking about understanding the fundamental workings of our planet.
Wow.
And of course, there are applications in security and defense.
Right. Remember Schneppet's example of detecting submarines?
Exactly.
How does that even work?
Well, quantum magnetometers are incredibly sensitive to the presence of metal.
Okay.
So they can be used to detect submarines' hidden explosives, even contraband hidden in cargo containers. It's like having the ultimate security guard constantly on the lookout for hidden threats.
That's incredible. It seems like quantum magnetometers have the potential to change so many aspects of our world.
Yeah.
But what about fundamental physics? Can they help us answer some of the big questions about the universe?
Absolutely. Scientists are even using them to try to detect dark matter.
Wait, dark matter. That's one of the biggest mysteries in science.
It is dark matter is this invisible stuff that makes up a huge chunk of the universe's mass.
Right.
But we can't see it or directly interact with it.
Right.
Some theories suggest that dark matter particles might produce incredibly faint magnetic fields.
Okay.
And quantum magnetometers, with their incredible sensitivity, could potentially detect those signals.
So we might be able to use these devices to solve one of the universe's greatest secrets.
It's a possibility.
That's mind-blowing.
It really is, and that's not all.
Huh.
Quantum magnetometers are being used to test some of the most fundamental symmetries in physics, like the equivalence principle, which says that gravity and acceleration are fundamentally the same thing.
Right.
They're even being used to study weird quantum phenomena like the Casimir effect,
Right.
where empty space itself can exert a force on objects.
My head is officially spinning.
Yeah.
But honestly, it's incredible to think that we can use these quantum effects to explore everything from the inner workings of the brain to the deepest mysteries of the universe.
Absolutely.
It's clear that quantum magnetometers have a ton of potential.
Yeah.
But what's next? What does the future hold for this technology?
Well, there are a lot of exciting developments on the horizon.
Okay.
Schneppet talks about advances in materials, science, quantum optics, and even artificial intelligence.
Okay, break it down for me. New materials, better optics, AI.
Mm-hmm.
How is all of this going to impact quantum magnetometers?
Well, for starters, researchers are always looking for new and improved quantum materials.
Okay.
For example, they're trying to create diamonds with even higher concentrations of NV centers, or materials that exhibit quantum properties at higher temperatures.
Right.
This would lead to even more sensitive and practical devices.
So it's like upgrading the hardware of the quantum magnetometer.
Exactly. And then there's quantum optics.
Oh.
Advancements in laser technology and the development of photonic chips
Right.
are going to lead to miniaturized, highly integrated quantum magnetometers.
Yeah.
Imagine a quantum magnetometer the size of a grain of rice
Wow.
that you could integrate into your smartphone or even implant in your body for continuous health monitoring.
That's incredible.
It is pretty amazing.
And what about AI? How's that going to play a role?
AI has the potential to revolutionize the way we analyze and interpret the data from these devices.
Oh, yeah.
Imagine algorithms that can automatically filter out noise, identify subtle patterns,
Right.
and even predict future changes in magnetic fields.
So it's not just about building better sensors. It's also about using AI to make sense of the incredible amount of data they generate.
Precisely. And when you combine those advances, better materials, better optics,
Right.
and smarter data analysis, I think we're on the verge of a quantum magnetometer revolution.
Quantum magnetometer revolution.
I like the sound of that. And think about the possibilities. Imagine a world where these quantum sensors are as common as GPS receivers,
Wow.
providing us with constant real-time information about the magnetic fields around us.
Right.
They could revolutionize healthcare, transportation, communication, even our understanding of the universe itself.
Okay, I'm officially a believer. This has been an incredible deep dive.
It has.
Thanks to Yorgo Schneppet's essay, we've been able to explore this amazing technology and all of its potential.
Yeah, it really is quite fascinating.
So for our listeners who are as fascinated by quantum magnetometers as we are, what's the one big question they should be pondering?
Here's a thought-provoking one. With all these advancements happening so quickly, how do you think quantum magnetometers will impact your life in the next decade? What new possibilities can you imagine them unlocking?
That's a great question to leave our listeners with. Thanks for joining us on this deep dive into the world of quantum magnetometers.
Absolutely. It was a pleasure being here.
Until next time, keep exploring, keep learning, and keep asking those big questions.